Hello, everybody. Welcome to the November CSE guest lecture. My name is Jamie Fine, and I'm the manager of the CSE. And today we are featuring John Voss, who's the other person on camera. So before we get started, I would like to go through the land acknowledgement. So we would like to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. And for me, I personally live on this land, and I would like to acknowledge that. So a quick note about who the CSE are. So the CSE stands for the Center for Climate Science and Engineering. This is a research and education center that's within the Civil and Mineral Engineering Department at U of T, and it was established in 2019. The CSE is made up of 7 faculty members. So Oya Mirkan is the director. We have Marian Hotzpalu, who focuses on transportation. Paul Kushner focuses on climate dynamics. Graham Norvell on health and process safety and chemical engineering and energy. Daniel Posen on life cycle assessment. Karen Smith on atmospheric science. And Marianne Tucci on building science. And then there's me, I'm Jamie Fine, and I am the manager of the center. So what do we all work together to try to do? Really the 3 components of what the CSE is going for is education. So education about both climate science and engineering. So teaching climate scientists the engineering perspective of what their work really impacts, and then teaching engineers how to use and understand information from climate scientists. And then on top of that, carrying out research at the intersection of climate science and engineering, and then hosting outreach events just like this one. So if you were here last month, you would have heard that we have an e-learning project going on. So we're developing a few modules that focus on different climate science and engineering lessons that are going to be integrated into university courses in the future. And if you're interested in being a student pilot tester for the modules, please reach out to that email address, cse.civmin@utoronto.ca. So feel free to reach out and you can be part of the pilot study. So that's one of the education things. We also have more outreach. So we have the last guest lecture of the year is going to be next month. It's Mikhail Chester, who's a professor from Arizona State University, and he's going to be speaking about future climate uncertainty in rigid models of infrastructure. That's the general topic. And that's going to be on December 15th at 5 p.m. on everyone's favorite meeting place or on the computer. And we're probably going to use Zoom. And if you're interested and aren't already getting emails from us, you can sign up to our mailing list at uoftcse.ca. And that's all the housekeeping for today. So now all that's left to do is introduce our speaker. The e-learning put in the chat. Of course, Edward, I will put that in the chat right after I'm done talking in 2 seconds. So just to introduce our speaker, so it's John Voss. He's a professional engineer, and he's also the principal of Jupiter Energy Advisors, Inc. John is a founding principal of Jupiter Energy Advisors. For more than 20 years, John has consulted for industrial consumers, commercial buyers, and a broad variety of public sector institutions and agencies, including the Ontario Energy Board and the Independent Electricity System Operator. He has given expert testimony in regulatory, civil, and commercial arbitration proceedings. John has a degree in chemical engineering from University of Toronto. He also has an MBA from the Schulich School of Business and a certificate in enterprise risk management. He has also earned a chartered director designation from the Directors College. And I think that I've summed up, enough to hand it over to you, John, and I'm really excited to see your presentation.
Absolutely. Thank you, Jamie, and good evening, everyone. As I was saying to Jamie a few minutes ago, I've attended a number of these over the years since you first launched the series, and I've always found each one very interesting, and I appreciate the opportunity to add to the discussion. I'll do my best to maintain the high standards of those who've presented before me. As Jamie mentioned, I'm an alumnus of the faculty, and as I was putting this together, I was thinking back. As a third-year student in chemical engineering, I took a course from the estimable Professor Donald Mackay, and it was entitled Energy, Environment, and Economics. And he first kind of introduced us as undergraduates to this triad and sort of helped us understand how environmental policy was energy policy and energy policy was economic policy, and the three were all inextricably intertwined in our society. And certainly to achieve our environmental goals, we need to change our energy systems. That's one of the key challenges that we're faced with today, and that has economic consequences. So those economic implications are many and they're complex, and I'm really sort of going right down to the nitty-gritty here in looking at a granular level of cost impacts at the operational level that are often overlooked when people are planning their transition pathway. So let me just share my screen and we'll get rolling here. Okay, so has everyone got my slides on the screen there, Jamie? We look good?
Yeah, it should be. I can see it.
Good. Okay, so as Jamie outlined, my perspective in presenting this is as an independent objective advisor to large consumers. We're sort of helping them make decisions that control their risks and their costs, and they're looking at their energy transition pathway and saying, what does this entail for me? For today's presentation, I'm focusing primarily on our work with institutional energy consumers. So many of these are characterized by having a large central utility plant like the University of Toronto does and other universities. Hospitals would fall into that category, district energy systems, that kind of thing. Often they have gas boilers, they have cogeneration facilities, chillers, et cetera, in their central utilities plant. These are interesting cases because all of the energy systems are really concentrated in one place at scale. And the opportunity there is to make a fundamental change in those systems that affect many buildings across the campus and a large amount of energy consumption, rather than the challenge of having to go to building and building and building to accomplish the same end. So they make a really interesting case to look at, and it's pretty optimistic. There's a lot that can be accomplished there. So while we have a number of clients in that area, my comments tonight are just representative. I'm not speaking on behalf of any client. I'm not presenting any client-specific numbers. These are just generic numbers to kind of illustrate the nature of the challenges that we face. The last speaker in this series, Dr. Roback, she emphasized from a sort of adaptation and resiliency perspective in buildings, how operating costs were often overlooked. People tended to focus on the capital expense that they faced, but overlooked the maintenance and operating costs. And that's really why we find the same thing happens on the energy transition pathway. People are mindful of the capital expenditure that they're facing, but the operating costs are kind of a wave of the hand, details. We'll get there. But my point, and the point I'll try and make tonight, is that you can't overlook those, and you want to think about them early. So some of the attitudes that you may encounter on the energy transition journey kind of fall on a spectrum. We hear some organizations, some people in some organizations that are saying, well, we can't do it, or we can't do it yet. The technology doesn't exist. The costs are too high, that kind of thing. Some of that is driven by perfectionism. Like there's no sense starting because we can't finish it. We can't go to zero. So why bother, or why get started now? We'll wait for better technology to come along. At the other end of the spectrum is this kind of naive assumption that we're going to get there. Don't worry about the details. But the challenge if you don't look at the details is that they will emerge eventually. And if they emerge in a way that you didn't expect, it's going to derail your plans. It's going to mean that it's hard to reach your objectives, and it may undermine the credibility of the whole mission in some people's minds. So in our view, we're aiming for this sort of pragmatic optimism. Let's identify what the challenges are early on, so we can apply our thinking to how to overcome those challenges and move forward. No surprises, or minimize the surprises as much as we can, so we know that we know what we're dealing with. So sometimes that sounds like we're being negative. It sounds like we're doubting or we're throwing up roadblocks. And I assure you, we're not trying to do that. It's important for organizations to have aspirational goals that they're motivating, they're energizing, they present challenges and stretch targets for us to meet. So we don't want to lose that, but we do need to put foundations under those aspirational goals so that they can be achieved, right? So that's really what we're trying to do, is put the underpinnings under those aspirations so that the substance of the challenge is clearer and the actions that are needed to realize the challenge are also clearer, and then they become actionable. So one of the challenges we encounter along that path are these, what I call dysfunctional assumptions. And a dysfunctional assumption is an assumption that's rigid or inflexible or leads you to counterproductive behaviors, something that's going to get in the way of you accomplishing what you're trying to do. So the challenge arises when you take a rigid framework, a frame of reference that you've carried for a long time, and when new information is presented to you, you sort of force fit that new information into your old paradigm. And that can lead you to make false conclusions about what that information is telling you, or what you need to do to overcome it. Just as our pilots here, if they're convinced they're in the cloud bank, then the goat is out of place. But they're going to have to think about, what does that goat really mean, and do I need to change my frame of reference? So the energy transition is a paradigm shift, and we have to sort of be prepared to critically challenge our assumptions going in. Old cost relationships and metrics that we may carry around in our head about what something's going to cost or what the impact is going to be maybe don't apply when we're making fundamental changes to our energy systems. And when markets more broadly are reflecting the fundamental changes that many people are making to their energy systems, those are all going to come back and reflect on us. So what I wanted to talk about tonight, there's many such dysfunctional assumptions, but given the time we have available, I'm focusing on just 3 that we commonly encounter. So there's a bit of I hope it's a bit of a myth busting exercise, perhaps. So the first dysfunctional assumption we want to tackle is the assumption that carbon costs, the pricing of carbon, the need to pay some compliance cost, will drive decarbonization. I should emphasize that I should have emphasized earlier that my comments here are mostly focused on the Ontario environment. And you did have a speaker, again, 2 or 3 times ago, Diane Sachs, who spoke about the carbon pricing regime generally and in Ontario in particular. And she went into much more detail than I will tonight. But it's important that we look at what's the real world impact of some of those policies, because a lot of organizations go into it thinking, I must decarbonize to avoid my carbon costs. And that's going to sort of justify, from an operating cost perspective, the changes I need to make. The fact is that for most users, electricity will remain more expensive than gas plus those carbon costs. And certainly for many large emitters, they fall under an intensity-based compliance regime that significantly blunts the impact of carbon pricing. So let me show some examples of what I mean by that. So the consumers, such as homeowners and small businesses, commercial establishments, pay for their carbon through a fuel carbon charge. And we're talking about natural gas. It's included on their gas bill. And they pay that price on every unit of gas they consume. And this, the charge is based on the escalating price for carbon that the federal government has set. And what this chart is showing is the light blue area at the bottom is the natural gas cost. So that's the cost of the actual molecule of natural gas that you would be buying. And we've projected that out to 2030. And that's just based on today's current forward price for that. That's what it's trading at now for that period of time. The purple band above that is the carbon cost on top of that. So if you're a homeowner, you're paying for both the gas and the carbon. If you're a small business, you're paying for the gas and the carbon for what you use. And you can see that carbon wedge is pretty significant. In fact, by about 2024, you're paying more for carbon than you're paying for the actual gas that you need to heat your house, so that you're tipping the scale there. And that's certainly going to have an economic impact. But if we compare it to the cost of electricity, even when we get out to 2030, when we've embedded a carbon price here of $170 a ton, according to the federal schedule, we're still ending up with gas costs of around just over $12 a gigajoule, or electricity costs equivalent of about 4.5 cents a kilowatt hour, where those same consumers would be facing the variable cost of electricity of about 9.5 cents a kilowatt hour. So now you obviously need to make efficiency adjustments between your gas burning equipment and your electrical equipment. If you had a heat pump, it would bring the efficiency of a heat pump would bring these costs much more closely into line. But that only starts to happen in the late 2020s, 5, 6, 7 years from now, when carbon reaches its maximum price, and only for those who have the most efficient electricity using equipment to replace their gas equipment. So this is the carbon pricing regime that many people will think apply to everybody, but even for those that it does apply to, it's not really enough to significantly drive someone to electrification, for example. On top of that, there's a more relaxed regime that applies to large emitters. Under the federal system, there's the federal output-based pricing system. And starting in 2022, that will be replaced in Ontario by an emissions performance standard, a made in Ontario carbon pricing regime. These are originally targeted for energy intensive, trade exposed emitters, manufacturers, industrial companies who, for example, face competition from offshore producers in their sector who don't face a carbon price. So it was meant to apply a carbon price to them, but in a light-handed way, so that it didn't significantly impair their competitiveness. But it also applies to other large emitters, many of those institutional consumers that I was talking about. So let's look at how that works. It's an intensity-based system. So it's based on your consumers are granted an allowance of emissions based on the units of output of their specific product. So in this case, if electricity is your product, under the federal system, you're allowed to emit 370 tons of CO2 per gigawatt hour of electricity production. Doesn't matter how big your generator is, because this is an intensity measure. It's not an absolute measure. So the first 370 tons of emissions are free. There's no carbon costs on those. Only if your emissions are above that would you pay. Under the federal system, any gas that's used for thermal output, for example, gas used in your boiler, would attract a carbon price. Under the Ontario EPS system, you have a greater allowance than the federal system for electricity output. But you also have an allowance for the total output of a cogeneration system, electricity and thermal output. And you also have an allowance for just thermal output from your gas boiler. The thermal output from the gas boiler is subject to what's called a stringency factor, where the allowance gets tighter year after year as we go forward. But you really get what I would call free emissions from all three sources. So again, it further blunts the impact that the economic driver to push people off gas. So how would this look? So for a case, what we're comparing here is a case for an organization that emits 50,000 tons a year in 2026, a few years from now, when the carbon price is $110 per ton. In this example, 70% of this organization's emissions come from the operation of a cogeneration facility, and the balance is from gas-fired boilers in the winter season. And we're looking just at their carbon emissions from scope 1, the natural gas use, basically. So if they were under the fuel carbon charge, they'd face a cost of $110 per ton on every unit of emissions, about $5.7 million a year. But they're more likely to be under the EPS system by that period of time. And because of the allowances that they're provided, their cogeneration production would have no carbon cost associated with it. They would be under the allowance in all likelihood. And they'd have a minor cost to pay on their thermal output. So they would only incur about $200,000 a year of carbon costs, or about $2 per ton when amortized over all of their total emissions. And that's just not enough to drive anybody to avoiding emissions costs. The federal output-based pricing system falls in the middle. It's more stringent than the Made Ontario one, but it does allow some wiggle room as compared to the fuel carbon charge. So the key takeaway here is that most large emitters are looking at that EPS threshold, and they're not seeing a price signal that's going to be enough to drive them off carbon. The second dysfunctional assumption, or area where we see people going astray, is when they project future costs that for their transition costs or operating costs post-transition based on extrapolation of historical costs. And this is dangerous for a number of reasons. First of all, your costs are made up of a mix of commodity market trading environment for natural gas and electricity, which are volatile, the price of which are volatile in the marketplace. The price of natural gas has almost doubled in the last 12 months, for example. Changes in usage patterns will affect your utility costs, and I'll touch on how in a minute. In Ontario, we have this artifact called the global adjustment, which is kind of the elephant in the room whenever anybody's doing anything with respect to electricity and electricity costs, and that has a significant impact here that I'll touch on in a sec. And then beyond the impact on you of your own changes, there's the impact on you of others' changes. As people change their consumption patterns, that will have market impacts, and that will reflect back on each participant in the market. So we'll touch on that too. So first, let's look at just the commodity price trends. So I've got natural gas and the hourly Ontario energy price, the price for electricity in Ontario, plotted on these charts. And the gas price, this dark line at the bottom, is again the currently trading forward price for that. It's not a proprietary forecast or anything. It's just what the market price is right now for each of those forward years. The line here for the hourly Ontario energy price is our projection, and it's based on some modeling we do, based on what generation there is in the generation stack and levels of demand and that kind of thing. So the key message here is you can see, particularly on electricity, how much higher electricity prices in general are expected to be in the latter part of the 2020s, for example, compared to what we've seen in recent years. So, for the last couple of years, we've had prices in the $13 to $17 per megawatt hour, whereas we're looking at prices in the 25 to 35, up to almost $40 a megawatt hour going forward, 2 to 3 times the electricity price. One of the key drivers of that on electricity is in Ontario, we have a large amount of nuclear capacity that's kind of base loaded. And then on top of that, we have hydro and wind resources. All of these have very low marginal cost or variable cost of operation. They tend to get dispatched first. And then natural gas generation sits on top of that generation stack and runs only when demand is high enough to need more supply than those other forms of generation can supply. Ontario is in the midst of a refurbishment program for the nuclear assets, and over the next decade, various units will be taken out of service for a period of time to undergo refurbishment. And at certain times, we'll have as many as 3 nuclear units in Ontario out at the same time for refurbishment. So that removes that amount of generation from the bottom of the generation stack and means we tend to call on natural gas more frequently. And natural gas has a higher variable cost of generation, and so we get a higher hourly Ontario energy price. Also in this is the retirement of the Pickering nuclear station, which should happen in 2025 according to schedule, and that just sort of goes completely out of the generation stack after that period. So the future is different than the past, and people need to factor in what the prices will be, not what they have been. Now, the global adjustment, I think, has probably been touched on in other presentations in this series, and it's the challenge with the global adjustment is when you explain it to a rational audience, they think you're joking, because it doesn't always make rational sense. But what's happening in the global adjustment is, in order to incent new generators to bring capacity into the market, the independent electricity system operator enters into contracts that guarantee those generators a certain revenue stream, whether they generate or not, basically covering their fixed costs and their required return, etc. If the generator is able to generate a lot of electricity at a high price, they'll earn a lot of revenue and they'll cover their revenue requirements and everything's fine. But if they don't generate a lot of electricity, or if the prices are very low, then they haven't earned enough in the market to cover their revenue requirement. And the IESO will top that up to whatever the contractual revenue guarantee was. The IESO then recovers those costs from consumers under a charge that appears on their bill called the global adjustment. It won't appear under that heading under your home bill necessarily, but that's how it's recovered from customers. So you can see that when the hourly Ontario energy price is low, the global adjustment costs will be high because we've got to make up what those generators are not making in the market. And when the hourly Ontario energy price is high, it probably means electricity demand is high. Those generators have been running a lot and earning a high price for their power. So they're getting most of the revenue from the market, and the global adjustment compensation will be lower in that market environment. Many of the contracts that make up the costs in the global adjustment will be expiring over the next several years. These are contracts that were entered into from the sort of 2005 to 2014 timeframe, 20-year contracts. So they're starting to come to the point where they'll be expiring. That will affect the amount of costs that are in the global adjustment mechanism and how they're recovered. And then finally, there's two different ways that consumers can pay the global adjustment cost, and how you pay the cost will affect the impact of the cost on you. So one of the first things to look at is the global adjustment costs will get lower. So if people are making assumptions based on historical costs, future costs will be lower. Largely that's because the hourly Ontario energy price is expected to be higher. But there's something else going on within the global adjustment. A lot of the costs in the global adjustment are sunk costs. They're costs that were, as I said, the result of contracts that were entered into in 2005. But the mechanism by which those costs are distributed spread those costs around all consumers in the market. Some of the charges are allocated for large consumers, are allocated based on how much energy I'm using when Ontario is at its peak demand, the 5 highest demand hours of the year. What's my share of that peak consumption? For small consumers like homeowners, the costs are allocated volumetrically. The dollars are amortized over the volumes consumed by those consumers. So the problem is, if I electrify my energy requirements and increase my electricity consumption, then my share of global adjustment costs will go up, because my share of the total consumption in Ontario, or my share of the peak demand when Ontario is at peak demand, will be greater. So I'm not simply paying the incremental cost of my incremental demand. I'm actually relieving you of some of your share of that historical costs. They're shifting over to me. So I'm taking a greater share of the historical costs, as well as whatever incremental costs I may be incurring on my own to increase my consumption. So that'll be a strong disincentive to electrification, the global adjustment. Widespread electrification of thermal demand will also shift global adjustment costs. The key issue here is that people often underestimate just how big Ontario's thermal demand is. The peak day send out for Enbridge, the gas distribution, the main gas distributor in Ontario, is equivalent to about 90 megawatts. So if you were theoretically to electrify that whole thermal demand, you'd require an electricity system of about 4 times as big as it is now to meet that demand. But to the extent that some of that thermal demand electrifies, we will see a shift in who's using electricity, how much they're using, and when they're using it that will affect their costs. So as I was saying a minute ago, for large electricity users, the global adjustment cost is allocated to them based on how much they're using in the 5 highest demand hours of the year. That's that ratio, that fraction, my peak demand in those 5 hours divided by Ontario's peak demand in those 5 hours gives me a factor that I multiply times the Ontario's global adjustment cost to determine my share of those costs. So consumers very carefully watch when is one of those peak demand hours going to occur. And what I'm showing on this chart is the historical frequency over the last 5 or 6 years of when those peak demand hours have occurred in Ontario. So I've got months across the bottom and the hours of the day up the side. And you see that the events have tended to occur in months 7, 8, and to some extent 9, July, August, September, the summer months. And they've tended to occur in the hours from about hour ending 16 to hour ending 19, late afternoon, early evening hours. So, you know, late afternoon of a hot July or August Wednesday is the kind of time that Ontario reaches its peak demand. So if my peak demand is at other times of years, I don't have to worry so much about attracting a large share of those electricity costs. But if everybody electrifies if a large number of consumers electrify their thermal demand, we'll see a shift where there'll be more winter peaks. And that'll affect a different class of consumer in a different way. And those who have a large thermal demand, if they have no means of mitigating that peak demand, will incur a greater share of the global adjustment costs, those historical costs, by taking them away from those who don't have a winter peak. I won't spend a lot of time on this slide. It's just getting into how some of the distribution rates can be affected. Distribution rates for both gas and electricity are made up of fixed costs and variable costs. And so the average unit price depends on how many units of consumption that those fixed costs can be amortized over. And so if your energy transition means that your load patterns change significantly, then the unit cost will change significantly. Your electricity use might look like it's shifting from the right-hand side there to the left-hand side. You're using electricity in more hours, more electricity in more hours. And so your load factor, if you will, is getting higher. Your natural gas use might look the other way, where you're only using it at peak times and not using it on a base load, for example, if you shut your cogen down, in which case your load factor will get lower and your unit costs will get higher. On to the last dysfunctional assumption, and this is a key one, and that is that all gas use is bad. The perfectionists tend to look for complete elimination of natural gas consumption if we're going to achieve our goals. But I think there's a case that can be made that the strategic use of gas for peak demand displacement it plays a critical role in mitigating decarbonization cost impacts and really makes it possible to justify or to get approval for certain projects. Without that peak demand displacement, the projects would look very daunting. So, for example, and this is largely driven by global adjustment costs and their impact on for large electricity consumers. But for example, if I used 10 megawatts of my own generation in just 140 hours of the year, when those high 5 events are happening, those high demand events are happening that determine what my share of global adjustment costs would be. By running my own generation and reducing my peak demand in those peak hours, I could avoid about $3.5 million in global adjustment costs at the cost of emitting about 300 to 450 tons of CO2. So to looked at another way, if I wanted to mitigate those 400 or so tons of CO2, I'd be looking at a cost of around $10,000 per ton to mitigate that each year in operating cost expense, if I was willing to pay the extra electricity costs. in order to avoid that natural gas cost. That's the kind of thing that makes, if you roll that, if you're not looking at that incrementally, if you're just rolling that into your overall project cost, you're saying, gee, it's going to cost us an awful lot to decarbonize. I'm not going to do it. The other consideration is to think about what's really happening when Ontario is at peak demand. As I explained before, we've got nuclear and wind and hydro at the bottom of the generation stack, and we have gas on the grid at the top of the generation stack, combined cycle generation at several large plants. So here's what's happening in those peak hours when I need, say, 16 megawatt hours of energy at my facility, and I'm taking it off the grid. There's going to be a combined cycle generator running somewhere, and it's going to need about 109 gigajoules of gas to produce 17 megawatt hours of electricity. It's going to emit about 5.4 tons to produce that amount of CO2 to produce that amount of electricity. It'd be about a megawatt hour of line losses, and I'll end up with 16 megawatt hours at my facility. If I turned on my own on-site generation, my cogeneration facility, to produce 16 megawatt hours of total output, I'd only need about 72 gigajoules of natural gas, and I'd only emit about 3.6 tons. So I'm avoiding 1.8 tons of CO2 if I generate the electricity myself. Plus, it's probably going to be cheaper because natural gas is cheaper than electricity. So I'm actually giving, the planet doesn't care whether the carbon comes from my facility or from the grid. It's just, can we produce less CO2? And that's what this strategy would do. It's important to keep this in mind because for the reasons I described earlier, where nuclear capacity is out for refurbishment, marginal grid emissions are projected to increase pretty significantly over the next several years. This is from the IESO's annual planning outlook. And what they're showing here is the marginal grid emissions. I have to stress that, not the average. So we're used to talking about how Ontario is has very low emissions factor, something in the order of 0.035, 0.04 tons per megawatt hour on average. What this is looking at is the marginal hour. So if I reduced demand on the grid by 1 megawatt hour, how many tons of CO2 would I have avoided by doing that? And this is the trend of that over the years. So you can see it rising pretty dramatically from 2021 out to the late 2020s. And then it starts to drop off after that as nuclear capacity comes back in with the refurbishments finished. So our grid is actually going to get a little dirtier in Ontario over the next few years. And this last chart looks at those same trends, but what we've done here is broken it out into different times of the year and different times of the day. So on the left-hand chart, we've got the summer months, and the light blue line is the on-peak hours. And you can see that, it kind of goes sideways. We use a lot of gas on peak in summer now, and we will continue to use a lot of gas on peak in summer. So any reduction in demand during the summer on peak hour has a beneficial carbon reduction impact. But today, right now, in the off-peak, so overnight and on weekends in the summer, we're not using a lot of natural gas. The demand is still, the capacity of the nuclear facilities is still enough that we can satisfy that demand in many hours without calling on the natural gas fleet to do that. But later in the 2020s, that will no longer be the case. So even in the off-peak hours, overnight and on weekends, natural gas will be running to meet that marginal demand. That last megawatt hour of demand will require natural gas generation. And then the chart on the right is the same for the shoulder months. So we're talking here spring and fall. And typically in the spring, we've got the spring runoff. We've got very windy spring and fall. So we're getting a lot of hydro, we're getting a lot of wind on top of the nuclear. But even that is not expected to be enough to mitigate this increase in carbon emissions. The last point I'll make on this, and then wrap up, is there's a challenge in this from a policy perspective. when organizations will be required to submit their carbon emissions information, their carbon compliance cost calculation, and they look at how much carbon is related to the electricity I imported from the grid. The emissions factor that will likely be specified for them to use for that calculation will be the average emissions factor. So as much as you can see that on the margin, you'd be avoiding global emissions, reducing global emissions by generating yourself rather than taking it off the grid. I'm not sure from looking at the carbon pricing policy that you will be economically incented to do it that way from a carbon pricing perspective. I think you'll still get dinged as if you increased your emissions if you operate that way. So that's perhaps a policy challenge for those who look at policy that would help to enable wiser use of gas-fired generation resources, whether they be on the grid or be privately owned. So let me wrap up at this point and get to questions. I think the key points that I wanted to make is that we're talking about fundamental change in the way we use energy, and when both the sources that we draw on and how we use those sources. And those changes are going to have wide-ranging cost impacts. It's a complex system that really needs to be modeled. And I think what we see happening too often is that people make broad assumptions. And it's not as though they're going to make more detailed calculations at some point. I think what we're encouraging is that it's better to do that sooner than later, because there are some intricacies, some nuances, some perversities sometimes in what drives those costs. And the magnitude of those costs are going to be a challenge. So the sooner you identify those costs and their magnitude, the better. So don't dismiss operating cost implications as a mere detail of the transition plan. It's not just capital costs you need to worry about. It's the operating cost impacts and how you can sustain those cost changes. And finally, people need to be open-minded, question long-held assumptions, be willing to look at things from a different perspective. How might we overcome that challenge? Maybe modify their initial plan of attack, not changing the objective, because the objective is an imperative, but changing how to get there in light of these realities, making sure that there's strong foundations under those essential aspirational goals. So that completes my prepared remarks, but I look forward to any questions